Recursive algorithms. Common patterns. Recursive algorithms are foundational tools in computer science, enabling elegant solutions to complex problems by breaking them down into smaller subproblems. Their ability to simplify tasks through self-similarity makes them indispensable in fields ranging from data structures to artificial intelligence. Despite their power, recursion requires careful design to avoid inefficiencies and errors. This article explores core patterns, techniques, and best practices for mastering recursive algorithms, tailored for developers seeking deeper insight into algorithmic problem-solving. Understanding recursion fundamentals. A recursive function calls itself to solve a problem, relying on two critical components, the base case and the recursive step. The base case halts the recursion, preventing infinite loops, while the recursive step reduces the problem size toward the base case. For example, calculating factorials recursively involves multiplying the current number by the result of the same function called with the next lower integer until reaching 0. Without a properly defined base case, even simple functions may crash due to excessive call stacks. The efficiency of a recursive approach depends heavily on overlapping subproblems and optimal division of labor. Problems like Fibonacci sequence generation often suffer from redundant calculations unless optimized via memoization or dynamic programming. Base case ensures termination, typically handles trivial inputs, e.g., n equals 0. Recursive step transforms the input into a simpler version of the original problem. Common recursive algorithm types. Several classic algorithms exemplify recursive paradigms. These include tree traversals, backtracking solutions, and mathematical computations. Each type leverages recursion's strength to handle nested or hierarchical data naturally. Tree traversal algorithms, such as in-order, pre-order, and post-order searches, rely on recursion to visit nodes systematically. Similarly, graph exploration via depth-first search, DFS, employs recursive calls to explore unvisited neighbors. Backtracking algorithms, used in puzzles like Sudoku or pathfinding, recursively test possible solutions while pruning invalid branches early. This technique is particularly effective for constraint satisfaction problems. Mathematical applications range from computing powers and combinations to solving recurrence relations like the Tower of Hanoi puzzle. Each scenario demonstrates how recursion simplifies inherently repetitive operations. Direct versus indirect recursion. Most recursive functions call themselves directly, but some employ indirect recursion, where function A calls B, which in turn calls A. While less intuitive, this pattern can model cyclic dependencies in systems like state machines or mutual recursion scenarios. Indirect recursion demands meticulous tracking of execution paths to prevent infinite cycles. It also increases debugging complexity compared to straightforward direct recursion. Tail recursion optimization. Tail recursion occurs when the recursive call is the last operation executed in a function. Languages like Scheme and Erlang optimize tail recursive functions to reuse stack frames, effectively eliminating stack overflow risks for deeply nested calls. In contrast, mainstream languages such as Java or C++ do not automatically optimize tail recursion, leading to potential stack overflow exceptions for large inputs. However, programmers can manually convert tail recursive functions into iterative equivalents for safety. An illustrative example is the factorial computation rewritten in tail recursive style using an accumulator parameter. This modification allows functional languages to execute the function efficiently without additional overhead. Memoization techniques. Memoization enhances recursive performance by storing previously computed results, avoiding redundant calculations. This technique is especially beneficial for problems with overlapping subproblems, such as Fibonacci numbers or shortest path algorithms. Caching mechanisms vary depending on implementation. Simple arrays or dictionaries can store intermediate values, while advanced frameworks provide decorators or built-in memoization libraries for convenience. However, memoization introduces memory overhead proportional to the number of unique subproblems solved. Balancing storage costs against computational gains is crucial for optimizing real-world applications. Dynamic programming builds on memoization principles, explicitly structuring recursive solutions around tabulation or bottom-up approaches for guaranteed optimality in certain contexts. Recursion in data structure manipulation. Data structures like linked lists, trees, and graphs benefit immensely from recursive processing. Tree operations, including insertion, deletion, and searching, leverage recursion to traverse hierarchies effortlessly. Binary search trees utilize recursive comparisons to locate keys efficiently. Insertion involves navigating left or right subtrees based on value comparisons until finding an empty spot. Graph algorithms such as DFS and BFS demonstrate recursion's utility in exploring connections. Although iterative implementations exist, recursive versions closely mirror natural descriptions of traversal logic. Handling circular references in graphs requires care to avoid infinite loops during recursion. Marking visited nodes ensures each edge is processed exactly once, maintaining correctness. Debugging recursive functions. Debugging recursive algorithms presents unique challenges due to nested call stacks. Traditional breakpoints become ineffective when tracing through multiple layers of recursion simultaneously. One effective method is logging the parameters at each recursive level. This visualization helps identify mismatches between expected and actual behavior, such as incorrect base case conditions. Unit testing plays a vital role in validating edge cases, particularly when dealing with extreme inputs that might trigger unexpected outcomes. Automated tests can catch off-by-one errors or missing termination criteria. Profiling tools help measure runtime performance, revealing bottlenecks caused by inefficient recursive designs. Profilers highlight frequent function calls and memory allocation patterns. Performance considerations. While recursion offers clarity, it often incurs higher constant factors than equivalent iterative counterparts. Function call overhead, combined with limited hardware optimization, can lead to slower execution times. Stack space consumption grows linearly with recursion depth, potentially exhausting available resources for deep recursions. In contrast, iterative approaches generally maintain fixed memory requirements regardless of input size. Some compilers apply automatic transformations to optimize recursion. For instance, C++s_attribute_optimize, O3, directive enables aggressive optimizations that reduce runtime penalties. Hybrid strategies combining both recursion and iteration can yield optimal results. Breaking down massive problems into manageable chunks prevents overwhelming the system while retaining conceptual simplicity. Real-world applications of recursion finds practical application in diverse domains beyond theoretical constructs. Web scraping routines frequently use recursive crawling to follow links across interconnected pages. File system navigation similarly relies on recursive directory traversal for batch operations. In bioinformatics, recursive algorithms assist in DNA sequencing analysis by aligning genetic sequences and identifying mutations. Pattern recognition in image processing also employs recursive filters for feature extraction tasks. Financial modeling utilizes recursive formulas to compute compound interest rates or simulate stock market behaviors over extended periods. Game theory simulations benefit from recursive decision-making processes that evaluate branching possibilities exhaustively. Artificial intelligence research continues pushing boundaries in recursive neural networks capable of learning hierarchical representations of data, a breakthrough enabling advancements in natural language understanding and visual perception systems. Educational resources for mastering recursion. Learners interested in deepening their knowledge have access to numerous educational materials. Online platforms offer interactive tutorials guiding users through hands-on coding exercises involving recursive functions. Books specializing in algorithms provide rigorous treatment of recursion theory alongside worked examples illustrating best practices. Textbooks such as Introduction to Algorithms by Corman et al. Contain extensive coverage of recursive methodologies. Community forums serve as invaluable sources for troubleshooting common mistakes encountered during development. Engaging actively with experienced practitioners accelerates mastery through collaborative learning experiences. Practice websites featuring curated sets of recursive programming challenges reinforce comprehension by exposing learners progressively difficult problems requiring creative solutions utilizing recursive techniques. Conclusion: this article has explored essential aspects of recursive algorithms, emphasizing patterns, optimizations, and practical considerations. By understanding fundamental principles and applying appropriate techniques, developers can harness recursion effectively in their projects. To deepen your expertise, experiment with implementing recursive solutions for familiar problems before tackling novel ones. Regular practice paired with analytical reflection will sharpen your ability to recognize situations where recursion provides superior clarity and maintainability compared to alternative approaches.